Okay, this is a good static equilibrium problem. We've got this girl here on this diving board. Way out here, the entire length is 3 meters. We've got this support kind of in the middle, a third of the way down. And then we got this other support that's going to try to balance out her weight over here at the left-hand side. We want to find both of these forces. So here's our setup. Pause the video and read that. Make sure you understand the problem. Okay, we're going to use static equilibrium. The sum of our forces will be 0, and the sum of our torques will be 0. The diving board is not moving, so it's not accelerating. It's not rotating, so alpha, our angular acceleration, will also be 0, which means the sum of our torques is 0. First off, all of our forces. We always want to put our weight vector at our center of mass. In this case, that's right at the middle of the board. That's going to be down. We've got the weight of the girl. And we've got a force from this little ledge here pushing down on the left side. And then the support in the middle will push up. So in magnitude, F1 minus F2 minus WB minus WD equals 0. F1's up, the rest are down. Okay, then the sum of our torques must be 0. We can pick our axis of rotation to be anywhere, and we'll still get the right answer. The easiest place, or the place I've chosen to put the axis, is right here at the end. Then any force that causes a counterclockwise rotation about this point A, we'll call a positive torque. Anything that causes a clockwise rotation, we'll call a negative torque. Okay, so then our torques will be F1 times that distance, force times distance, and that's a positive torque that tries to rotate us counterclockwise. F2 is a distance 0, so F2 times 0, that'll be a 0 torque. WB tries to rotate us clockwise, so that's a negative torque. So WB times our distance, and that's negative. And then WD, the weight of the girl, times our distance, that's also a negative torque because it tries to rotate us clockwise. So the sum of the torques equals 0. So just quickly solving, we get F1 is 1950 newtons, and that points up. And then using the sum of our forces, using this equation, we can find F2 and get 1160. We could have also, instead of using this force, or this sum of forces equation, we could have started over and put the axis of rotation maybe in the middle, and then done sum of torques again, and we could have solved for F2 that way. A lot of different choices here. I do want to point out, look at these forces, 1950 and 1160. That's much more than the total weight. The total weight on the board is only 790, the board itself and the girl. The force here was 1950 newtons, more than double, or almost double, the weight of the board and the girl together. It's a tremendous amount of force right here because of the sum of the torques. We've got a lot of force here that's holding everything up. That's all going to be balanced out here. So a tremendous amount of force here. These boards have to be really strong or they'll break.